the computer. Hi, everyone. Thanks for joining us. Today, we are happy to have Alex Belin from CERN, Geneva, to give us a talk on the OPE randomness hypothesis and the Euclidean wormholes. Alex, please.
Awesome. Thanks a lot, Nima. Thanks, everyone, for coming and for the invitation to speak today. So my talk is going to be based on some work that came out over the last year or so. A first paper with Jan de Boer at the University of Amsterdam from last summer, and a more recent paper from a few months ago, also with Jan and with Julian Sonner and Pranjal Nayak, who are both at the University of Geneva. And as you can see on my slide, I put it in big. And I know we're all used to virtual seminars by now, but please really stop me, interrupt me, ask questions, and let's try to make the talk as informal as possible. And I think that way it'll be better for everyone. Great. So let me dive in. My talk today is going to be about the ADS-CFT correspondence. And what this duality states is that the partition function of a conformal field theory, in that it's the generating function of all correlation functions of a conformal field theory, is equal to a partition function of a theory of quantum gravity in anti-de Sitter space. The theory of quantum gravity here on the right-hand side in all examples that we know of ADS-CFT is quite complicated. For example, the most canonical example is type 2b string theory on ADS5 cross S5. But in certain parameter regimes where we understand ADS-CFT the best, which is, when there's a large number of degrees of freedom in the CFT, and that the CFT is also strongly coupled, then this gravity theory on the right-hand side of the duality here admits an approximation in terms of a low-energy effective field theory. And this low-energy effective field theory is simply that of general relativity. So let me maybe just write down the Einstein-Hilbert action here. And of course, there could be couplings to matter fields. Really, in the canonical examples, it's not general relativity, but rather supergravity. But let me just schematically include that into S matter. And sort of the main question that's going to be driving my talk today is to understand, well, what part of the CFT dynamics can we access with this lower energy effective field theory. Or maybe to phrase it slightly differently, one could say, what is the CFT dual of the bulk low energy effective field theory? Okay, so those will really be sort of the central questions driving my talk today. And of course, we've gained quite a bit of knowledge since the early days of ADS-CFT, and I'll sort of review what we've understood about this question in steps of increasing complexity. So let me start by the first step, and this is what we would call standard or maybe perturbative effective field theory. And one thing you can do, you can take your low energy effective action, the Einstein-Hilbert action, and you can take fields and expand them around the background, where G naught would just be the ADS metric plus some perturbations. And you can expand to any order in these perturbations and compute low point correlation functions of the dual operator. Okay, so for example, a 4-point function of scalar operators in the CFT would be computed using Winton diagrams. So to leading order, we would just have disconnected diagrams of this type. Then at higher orders, there's connected diagrams, for example, a contact 4-point diagram here, or you could also have exchange diagrams. And then at higher orders, you would have loops and so on and so forth. And what we now understand fairly well is that there's a map between parameters of the low energy effective field theory, like masses, 3-point couplings, 4-point couplings. There's a map between these parameters and the data of the conformal field theory. And the data of a conformal field theory is a list of operator scaling dimensions and their 3-point couplings. And so there's a map between these parameters in the low energy effective field theory and the data of the CFT, and this is understood in the 1/n expansion. Okay, and in particular, what you would extract using these Witten diagrams are anomalous dimensions to double trace operators of the dual CFT. And I think one thing that's important to stress here is that the map is exact. Okay, so there's certain parameters in the low energy effective action, for example, a 3-point coupling, and we can exactly map that to some data in the dual conformal field theory. Okay, so this is sort of the simplest, the simplest thing you can do. It's sort of perturbative Witten diagrams, which are the equivalent of perturbative scattering amplitudes, but in anti-de Sitter space. And this is really, the bread and butter of low energy effective field theory. Now, of course, that's not all we can do. We can do a lot more. So the next step is
Alex,
sort of, yes, question. Great.
What do you exactly mean that you say when you say the map is exact? What is the...
Great. So what I mean is, for example, here's maybe how I could write it. So there's a set of multi-trace operators. For example, there's some operators. If there's a single trace operator O, then there's also a multi-trace operator O. And the scaling dimension of this operator O squared would be equal to 2 times the scaling dimension of O plus an anomalous dimension divided by n squared. And what I'm saying is that, for example, this anomalous dimension can be mapped exactly to parameters in the low energy effective action. For example, a quartic coupling. So for example, if you had in the bulk EFT, something like d phi, so just a kinetic term, a mass term, and then a quartic coupling, we now understand exactly how to do the map between gamma and lambda here.
I see. Thank you.
Okay, and this is not approximate. This is exact. Of course, there's higher order corrections to the anomalous dimensions, and those are more complicated. But at this level here, we can make the map exact. So really, whatever that parameter is, you know exactly what the associate anomalous dimension is in the CFT. And a similar statement holds for OPE coefficients. Thanks. Yes, this is great. Please continue asking questions. So as I was saying, this is sort of standard perturbative effective field theory. But we also do a lot more with the low energy effective action. And in particular, we consider black holes. So one thing that you can do is you can use the low energy effective action, look at its equations of motion, and then look for classical but nonlinear solutions to the equations of motion of the low energy effective field theory of SEFT. Okay, and using the standard dictionary of ADS-CFT, the partition function, the CFT is approximately given by the on-shell action of the gravitational solution. Okay, and so this is a way to get an approximate answer for the partition function of the CFT, and there's various quantities that you can extract from this. The most famous is the entropy, and this formula has a name. It's the Beckenstein-Hawking formula for black hole entropy. And this is one quantity that you can extract this way. And once you have an entropy, well, it's very natural to define a density of states just by exponentiating the entropy. And now, so you know, the gravitational effective field theory gives you access to this quantity rho bulk, but you can ask, how is that related to the actual CFT density of states? And a conformal field theory, or most conformal field theories that we like, are compact. They have a discrete spectrum. However, what you compute using the gravity side of the duality is a continuous function of the energy. So you can ask, how is rho bulk related to rho CFT? And this is where things stop becoming exact. There's some coarse graining happening. And really, you know, the bulk density of states, you should think about it the following way. It's given by some energy. It's a function of the energy, or mean energy E bar. And then what you really do is integrate the CFT density of states over some energy window centered at E bar and of size, which you can sort of choose, but typically you can take it to be the microcanonical window. And really, you know, rho CFT itself, there's a discrete spectrum, so it's a sum over delta functions. But if you coarse grain that or average that density of states over a sufficiently large energy band, then you obtain a smooth function of the mean energy E bar. And that's really how you should think about what the gravitational theory is extracting for you.
Alex.
Yes.
So E to the power of S black hole, we usually think of that as a canonical partition function. So to get the density of states, you have to do the inverse Laplace transform, right?
Oh, thanks. Yes, absolutely. Yeah.
So what you're doing here is just like you're simplifying that inverse Laplace transform a little bit, because you know what the answer is going to look like, right? Okay, I see.
Yes. So
this
you're
is
right.
Not literal, yeah.
No, this is actually fairly important. What gravity really has access to are not really. So what I've done here is sort of micro-canonical, whereas what gravity really has access to are more like canonical things, like the finite temperature partition function. And you're right that to extract the density of states, you need to do an inverse Laplace transform. And what I've written here is sort of the saddle point evaluation of that inverse Laplace transform.
But the coarse graining in these two, coarse grainings, once you start talking about coarse grainings, you are talking about averaging out over a lot of non-perturbative, like energy gaps that are exponentially small, right? So
that's right.
Those details, I feel like this matters, that you do the inverse Laplace transform as opposed to saddle point approximation. But maybe you could go ahead and we'll discuss this further.
Yeah. No, I think I agree. It does matter. And you know, really, if you were capable of getting the full thermal partition function and doing the exact inverse Laplace transform, you would be able to access this. But the problem is that we can't do that exactly. So you know, we compute things approximately, and then we do various saddle points. And so the thing you have access to looks a lot closer. I mean, will be an object of this type. Rather than the exact density of state. You can't resolve the exact spectrum.
I mean, you could have done this exactly as well, right? Like you could have inverse Laplace transform if you assumed simple phases. If you didn't assume like small black holes or something, then...
Well, that would have required, you really have to, you really, to do the inverse Laplace transform requires you to know the partition function as a function of complex temperature, and to exponential accuracy, let's say. As
a function of temperature, right?
Yes.
Yeah. Not necessarily, not complex temperature. Yeah. So what?
Well, I mean, the inverse Laplace transform, the contour is slightly.
Right, but that's analytic continuation. All that data you need is the real data.
Yeah, absolutely.
Yeah. Okay. Thank you so much.
Yeah, I mean, I remember a few years ago, people were giving talks. I don't know, maybe Europe, but I don't remember where they computed or tried to compute the entropy of a black hole up to getting an integer number, computing all these corrections. I don't remember who was doing that, but it was particular black holes.
Absolutely, yeah. For supersymmetric black holes, in some cases, you can actually do this, and a lot of the time it involves localization. But there's some cases where you can actually get integers out. But those are, I would say, very special black holes. And if we just take a generic Schwarzschild non-supersymmetric black hole, then we don't expect to be able to get those integers.
But that's what you need to do if you want to do, I guess, what Nima wants or something.
Yeah, the exact thing somehow. Yeah, that's right. Great, thanks. These are great questions. And of course, once we have the black hole background, we can do more with it. And one thing that we can do is compute, for example, a 2-point function on the black hole background, which would be a diagram of this type. And a particularly nice 2-point function to consider is the finite temperature 2-point function separated in Lorentzian time. You should put an L here. And the answer that you'll get from the black hole solution is something that looks like this. It'll start off and it'll decay, and it'll decay to 0. And this decay here you can think of as being related to thermalization, or in the gravity language, this is quasi-normal mode behavior on top of the black hole solution. But we know actually that this curve cannot be the true exact answer, because any CFT with a discrete spectrum actually will not be of this type. And once the signal becomes exponentially small in the entropy, it will start to go through some crazy erratic oscillations, and it'll stabilize at a value which is exponentially small. Okay, and this is due to the discrete spectrum of the CFT, or to this density of states that I wrote here. But this is something that we cannot capture using the black hole background. And this is a form of the information paradox that Malacena put forward, I guess, close to 20 years ago now. Okay, so this was sort of the second step. It's beyond perturbative EFT, but it's considering classical nonlinear solutions to the equations of motion. And this brings me to the third level of complexity. Yes.
Can we go? So
yes.
When you say it will stabilize around E2 minus S, will literally, yeah, like how do you, will it literally like asymptote, or there will always be fluctuations, right?
Yeah. So there's always absolutely, but sort of the mean value around which it fluctuates is essentially e to the minus s, and it will do so for a very, very long time.
What controls the size of those fluctuations?
Great. I'll try to talk about that a bit later, actually.
Okay, thank you.
But I think, roughly speaking, in this particular case, they're kind of as big as the signal itself. So
this is exactly what my problem is, right?
Yeah. So this is a cartoon, and we'll get to that. We'll get to that later in the talk. Yes, this is a great question again. Yeah. So this is really this is not to scale. These are cartoons. Great. So great. So the third step.
Actually,
is
sorry,
now,
Alex.
Sorry, one more question.
Yeah. So if you literally plotted this for a bunch of qubits,
yeah,
you will not see E2 minus S flattened thing, right? You agree? Because the fluctuations are the order of E2 minus S. So you need a large parameter to make sense of such a thing.
Yes, you mean if you pick some chaotic spin chain and we'd stop at of 5 qubits or something like that?
If you don't have a large number of spinners, you will not get an E to minus S even averaged out thing.
Yeah, so you're right. Yeah, this should be really thought of as what's happening in the thermodynamic limit. If you're in a small Hilbert space, it'll be hard to separate. Everything's order 1. It's hard to separate anything from anything else. I think.
Thanks so much. Sorry for interrupting.
Yeah, no, absolutely. I should say that for a field theory that has a field theory always have an infinite number of degrees of freedom, and so for a field theory you could still get an exponential suppression by just going to very, very high temperatures, even if the field theory has an order 1 number of degrees of freedom. Great, thanks. These are all great questions, and this is not too much. Please continue like this. This is what a seminar should be like. Great. So the third step is now to go way beyond what you might have thought EFT has access to. And this is what now involves wormholes or Euclidean wormholes. And this is related to discreteness of the spectrum. So there's a quantity that's very closely related to the thermal two-point function at Lorentzian separations that I wrote before, which is called the spectral form factor, which is, you know, the square root of analytically continued partition functions as a function of temperature, which people in quantum chaos and random matrix theory like a lot. And again, this object is you know, very similar to the one I drew before. And it has the feature that these erratic oscillations start, they grow linearly for a time, and then they stabilize. Okay, and this feature are called the ramp, the dip, the ramp, and the plateau. And in a really nice paper from a few years ago, Sad, Schenker, and Stanford realized that actually, at least for low-dimensional models of gravity, in particular for two-dimensional gravity, JT gravity, you can extract some features of this erratic signal by considering wormholes that asymptote. So these are Euclidean geometries that asymptote to two disconnected Euclidean boundaries of the conformal field theory. So, you know, here there's a beta and here there's a beta prime. And if you include these types of configurations in your gravitational path integral, then, well, you can't quite reproduce the exact ramp, but you can sort of reproduce its mean. Okay, so this is the ramp, so you can reproduce the mean of the ramp using these types of geometries. Okay, and this is really exciting because this ramp is related to nearby eigenvalue repulsion in chaotic Hamiltonians, and it's, you know, some sort of universal feature of quantum chaos, and so you can extract, you know, some universal property of quantum chaos using only the low energy using only the low energy effective field theory. And really the thing that you're probing, the thing that you're sensitive to, is discreteness of the spectrum. Okay, and this is sort of way beyond our wildest dreams of what we thought the low energy EFT could ever have access to. And I should say that this is not unrelated to all the progress around Hawking's information paradox, and in particular reproducing a unitary page curve, where there are other types of geometries which are closely connected to these ones, which are called replica wormholes. And there again, you know, the inclusion of these geometries give you, you know, some sort of window into the dynamics of the theory in some very sensitive way, and in that case, can give you a black hole evaporation curve compatible with unitarity. Okay, so it seems like if you know, allow yourself to have access to these Euclidean wormholes, you have a window into a lot more about the dynamics of the conformal field theory than what you would have thought you had naively access to.
Oh,
however,
sorry, Alex.
Yes, question.
So here, what is you have in mind? You don't have an ensemble of Hamiltonians. You're talking gravity, right? So these are gravity partition functions. So what is beta prime here? What is this?
Oh, here it's the boundary conditions for your gravitational path integral. So, you know, you sort of say, let's look at all the gravitational configurations that have two Euclidean boundaries, one of size beta, one of size beta prime.
But what the quantity you're trying to compute, that f of t, which is z of beta plus it, would not include such a term in it, right? Each z of t, according to their laws of ADS-CFT, you will have one boundary, you do the path integral, right? You analytically continue and such. Well,
that's sort of one of the things that I'll be discussing today, is try to understand a bit better what the rules are. But, you know, I think that the rules of ADS-CFT are to say, okay, here are the boundary conditions. Look for all field configurations that satisfy those boundary conditions. And so when you have two disconnected Euclidean CFT spaces, of course, what you're saying is true. There's also all these other types of configurations where you just fill in, you know, the two cycles at the boundary. So here's beta prime, and you can just fill them in by forming disks of this type. But of course, you know, in principle, if you put two of them, well, you should also allow gravitational configurations that extrapolate between the two.
I guess that's the question I'm asking.
Yeah.
Why? You know, the f of t, if I look at f of t, right?
Yeah.
That is not some quantity that has two boundaries. That is a quantity that has one boundary that I'm evaluating at two different values of beta.
Right.
Right? If you're not doing any averaging or anything, this is just, like it shouldn't matter how many z's this is a function of z of beta, right?
Well,
Not allowed to change the rules of the game.
Yes. So, well, maybe you can let me go to the next slide, because this is sort of, this is sort of the whole question. And I think it leads me exactly to what I'm going to come to, which is related to what you're bringing up. So the problem is that there's a price to pay in this story. And in fact, I haven't really taken the chronological route to wormholes, because before realizing that they were useful, we were actually very confused about them. And this is due to a factorization problem. And this was raised by Maus and Maldacena. And the problem is the following. So I'm going to go through the same logic that I guess Nima was disputing a while ago. So say we want to compute the product of partition functions in the conformal field theory. And now we say, let's use ADS-CFT and let's compute this in the gravitational theory. And the problem is that if you allow configurations, which are of this type, which asymptote between two boundaries, beta and beta prime, and you compute the on-shell action of the solution, you'll get some answer. It's going to be some function of beta and beta prime. But this is not equal to other functions, f twiddled beta times beta prime. Okay, and typical, it's some complicated function. It could be a function of beta plus beta prime, for example, or beta minus beta prime. And it's not equal to just the product of two functions of beta and beta prime. However, of course, a CFT partition function, if you just take two disconnected Euclidean spaces, the two CFTs don't talk to one another. And here in the conformal field theory, you clearly get a manifestly factorized answer. So here there's a mismatch. And this is a puzzle. Okay, and this is a puzzle that was raised many, many years ago. So to come back to Nima's question, I think that the perspective back then was, well, maybe we should not include these types of solutions in our gravitational path integral, at least not without something like disorder averaging over the Hamiltonians. And we should only consider disconnected spaces, and we should just, compute z of beta times z of beta prime, and forbid these types of geometries. And I think that what we're learning somehow is, as I sort of saw on the previous slide, is that, well, maybe that's right, but if you do allow yourself to include these geometries, then actually you're learning something about the theory anyway. Okay, but you're learning something about the theory, you're getting this sort of averaged ramp, but you're not getting the exact erratic signal. And the fact that you're not getting the exact answer is also why you have this mismatch. So, the price to pay is the lack of factorization, which might confuse you, but it's really there because it's trying to teach you something about the dynamics of the theory. And sort of the goal of my talk today will be to give some sort of unified framework to explain this. In other words, give a framework that's capable of reproducing 1, 2, this we sort of understand, but now also 3. Okay, and that's what I'll really try to do. And so let me just go over the plan for my talk, and then I'll see if there's any questions. Oops, outline. So this was my introduction. Then I'll start by a lightning review of the eigenstate thermalization hypothesis. And then I'll introduce the OPE randomness hypothesis and tell you why it's useful. And then depending on time, I'll discuss either 1 or 2 applications. The first one is the genus 2 wormhole, which was one of these confusing wormholes that Maus and Maldacena talked about in their paper from many years ago. And the second one, we'll see if I have time or not, is to give an argument against global symmetries in quantum gravity. from these wormholes. Okay, so that's the plan for today, but let me just stop and see if there are any questions. Okay, if not, let me dive in, and of course, you can stop me at any time. Very good. So let me start by a review of Diagon state thermalization hypothesis of ETH. So what ETH says is consider a quantum chaotic many-body system and look at the matrix elements of simple operators, by which we mean few qubit operators. Say you have a large a spin chain, and you look only at simple operators that act on a few spins. Then these matrix elements have a universal structure. They're given by the following type of ansatz. And I'm going to introduce all these various quantities very fast. Okay, so E bar is just the average energy. Omega is the energy difference. F, A, and GA are smooth functions of their arguments, and they're related to microcanonical 1-point and 2-point functions. And Rij are erratic numbers. So they're wildly fluctuating erratic numbers, which are basically Gaussian random variables, meaning that they have zero mean and unit variance. And I should say that I've written this in a form that's slightly non-canonical. Typically, we actually know the size of this function g, and it's very small. So typically, people pull out a factor of the entropy and write it in the following way with now g twiddle of order 1. And so what ETH is really telling you is that if you look at these matrix elements in a chaotic many-body quantum system, then on the diagonals, you have large entries given by the microcanonical 1-point functions. And on the off diagonals, you have very, very small numbers, which are exponentially suppressed in the entropy, times some smooth functions of the mean energy and energy difference. Okay, and this is supposed to be some sort of universal feature of all quantum chaotic systems. Okay, and that's what ETH tells you. But
that's only for some operators, I think so.
Sorry?
It's only true for some operators.
Yes, absolutely. For simple operators. Yeah. Like, let's say a few qubit operators. Actually, I'll come back to complicated operators in just a second.
Can I
yes?
When you say Rij are wildly fluctuating, what is, just to be clear, what do they depend on? What are they fluctuating in? Is it like in time, or is it in E bar and omega?
No, they're numbers. So imagine picking energies in the microcanonical window. So you have a matrix, which is e to the s by e to the s matrix, and you look at these numbers and you plot them. For example, well, I'll come to this in a second, but in some case you could imagine solving for the Hamiltonian and now plotting these numbers, and they're just going to go like crazy. They're going to be like random numbers, but if you start averaging over them, then you'll see that they have zero mean and unit variance. So they're like random variables that are drawn from some ensemble, if you want.
Okay. So they're just sort of pseudo-random.
Yeah, they're pseudo-random. Yeah. So exactly, that was going to be my first comment, and it's that in any fixed theory. Rij are actual numbers. They're not random. They're actual numbers that, like I just said, you could imagine if you were very powerful and had a very strong computer, you could imagine diagonalizing the Hamiltonian, solving the theory, and computing these numbers. But the point is that for many practical purposes, you can treat them as random variables, which statistically have zero mean and have unit variance.
So, Alex.
Yeah.
Here's a confusion of mine. I've always had this confusion. So, the version of the statement that where you said this is a random matrix sitting there. This is some sort of a statistical statement. It's sort of saying that the probability that this E of I, O, A, EJ, whatever, this quantity, this expectation of the diagonal matrix element is given by this expression, is bounded above and below by FA of E delta IJ plus some exponential corrections, is given by some probability distribution, right?
Yeah.
Now, what is the ensemble here? When you say probability, you have an ensemble. Do you have in mind, and yeah,
it's an ensemble of states. So it's, imagine, so we're in the thermodynamic limit. These energy eigenstates have a lot of energy. They have, say, finite energy density, but their energy, so their energy is going to infinity, but the energy density is staying finite in the thermodynamic limit. And now we're going to bin, let's pick our favorite mean energy, and then we're going to bin, the microcanonical window. So we're going to look at e to the s states over 2 above and below that mean energy, right? And that's the energy bin that we're going to look at. And we're going to ask, okay, well, now what are the statistical distribution of these numbers within this matrix? And
sorry, go ahead.
So so it's statistical in that sense. It's that, it's a matrix of numbers, and if you start averaging over the columns or the rows, or you look at, how these numbers are distributed, well, they have some statistical distribution.
So it is somewhat like you have infinite number of copies of the theory, and then you could make it rigorous in the large number of copies of the theory as a large number of copies statement.
Yeah,
no, never mind.
I think,
go ahead.
Yeah, this is a very subtle question, and so ETH is really statistical, and you can ask whether or not you can make ETH exact or not by, like you said, taking many copies of the system. And the answer is, I don't know. You can ask, how does ETH fit in with random matrix theory? And I think what I would say is ETH is slightly more than random matrix theory. There's a version of ETH that follows just from looking at, random matrices and thinking about O's as random operators acting on this microcanonical window. But there's more in ETH. There's more data in ETH than what is in random matrix theory. And so, so the numbers are not truly random, but they're rather statistically random.
Yeah, my general complaint, which is not to you, but to this statement of the theorem, is that it's not a mathematically rigorous statement as it is.
I think I absolutely agree. I think I absolutely agree, and I'm still trying to fully understand what it means, but I think I agree. It's not mathematically rigorous, and it's not exact. Yeah, I agree. It's still useful nevertheless, and
no doubt about that. Yeah.
But yes, I think I agree with you. Yeah, and I've been very confused about this myself. Great, and let me just come to the second comment. Is that in general, and more or less all of the time, the RIJs are not Gaussian. And contrary to what you might hear sometimes, that their distribution is not Gaussian. And the point is that what ETH guarantees you is that you correctly reproduce, thermal or microeconomical 1-point and 2-point functions. But of course, there's also higher point functions, 3-point functions, 4-point functions, and so on and so forth. And so to reproduce those, you need non-Gaussianities. But the Gaussian distribution is the leading approximation in the sense that if you look at how big the non-Gaussianities are in individual elements Rij, the non-Gaussianities due to a connected k-point function are of the size minus k minus 1 over k times the entropy. Okay, so as k, so this is further and further exponentially suppressed in the entropy as the number of connected correlators go. So, the Gaussian distribution is the leading distribution or the leading effect, but, the relative weight of the non-Gaussianities are smaller and smaller and smaller. Of course, when you compute 4-point functions, you have to sum over more intermediate states. So, it very often happens that the non-Gaussianities give contributions that are just as big as their Gaussian part in 4-point functions. But still, as in a distributional sense, the non-Gaussianities are suppressed. Okay, but they are there and they're important. And there's papers, for example, discussing their role in out-of-time ordered correlation functions.
So, sorry,
Sure.
Alex, just
Yeah.
to make sure I understand this correctly. So you are making the statement that the one-point function of simple operators is given, the probability measure that controls it is the Gaussian in a chaotic theory. One-point operators, one-point functions.
Is to leading order is a Gaussian distribution.
Leading
Yeah.
order in what?
In the entropy. So, what I'm saying is that there's this matrix.
Yeah, okay.
So I'm saying that there's this matrix Rij so the off diagonals are given by this. And then you can, if you want, you could subtract that out of the Rijs and define something that will be useful for 4-point functions. And then the off diagonals of those will be even further suppressed. They'll be of size e to the minus, for 4-point functions, s 3/4 times s.
So for example, like for 1-point functions, should I write e to minus, say, s of e over 2? What's the coefficient I put in there?
Oh, here?
For
You mean
no, the second, the suppressed ones.
Oh yeah, the suppressor. So the idea is the following: is that really Rij RKL is delta Ij delta Jk plus e to the minus s with some coefficient here.
The coefficient is what I'm asking actually.
Oh well, you have to reverse engineer it from here. The one that you would need for connected 4-point functions would be suppressed by e to the minus s over 4, and then if there's two of them. If there's 2 of them, I think it would be e to the minus s over 2.
So for 1-point functions in particular, it would be also e to minus s over 2.
Yeah, so assuming the 1-point functions are order 1, you can already see that there's a suppression of e to the minus s over 2 from the diagonal to the off diagonal. And then what I'm saying is that the further ones would be further suppressed by this thing down here. Meaning that if you now start averaging, 2 R's over the energy band, you would get these product of Kronecker deltas plus a correction that would be e to the minus s over. So really what one should write here is the following. Really here there's a sum over k, ak, or maybe I should call it gk. These are again smooth functions times e to the minus k minus 1 k times s or something like this. And these are responsible for the non-Gaussianities. These are the non-Gaussianities. Does that help?
Yes, thanks so much.
Great, thanks. So this was all about quantum many-body systems, but you can ask what about conformal field theories? Okay, and as Nima wrote some very nice papers on this already a few years ago now, there's something special about CFTs. Which you don't have in other quantum systems, and that's the state operator correspondence, is that energy eigenstates can be mapped to local operators. And so, this matrix element is really nothing else than a 3-point function in the vacuum, in other words, an OPE coefficient. Okay, but of course we have to remember that OA needed to be a simple operator and that the energy of these states needed to go to infinity. We need to be in the thermodynamic limit. So these 3 operators are not all on the same footing. These operators, OA is a light operator. So what we mean by a simple operator is that, the scaling dimension of this operator will be fixed in the thermodynamic limit. Whereas OI and OJ, they're heavy, meaning that their scaling dimensions scale in the thermodynamic limit. So really, the way you should think about ETH and conformal field theories is in terms of heavy, heavy, light OPE coefficients. Okay, so really it's a statement about the statistical distribution of OPE coefficients, if you want. But once you've understood that, then it's very natural to ask, well, what about other types of OPE coefficients, like heavy, light, light, or heavy, heavy, heavy? What can we say about these? And this is what led Jan and I to conjecture the OPE randomness hypothesis. And what we sort of conjectured is that, in any chaotic CFT, then these other OPE coefficients also have some ansatz in terms of random variables. Okay, and the idea is that here Ri and Rijk are again random or quasi, let me call them quasi-random variables. Of unit variance and zero mean. And of course, the fact that I'm saying that their unit variance is a little bit, I'm cheating in some sense, because really what I did is I pulled the variance out into these functions here and there. Okay, so this is the conjecture that we put forward. And it turns out that in 2D CFTs, well, several things are true. First of all, these functions, one has access to these functions because they're fixed by conformal symmetry. FAB is fixed by 4-point functions on the plane and crossing symmetry. And F is fixed by the genus 2 partition function plus modular invariance at genus 2. And in fact, in a nice paper by Collier, Maloney, Maxfield, and Saris, they even showed that there's actually a universal way to get these access to these functions, and also to the off-diagonal functions, to G, the G that was sitting in ETH. All of these three are you can get them in a unified way using what's called the Virasoro crossing kernel. And so they already had guessed that there was some type of extension of ETH that holds in 2D CFTs. And what we're really conjecturing here is that, in any chaotic CFT, in any number of dimensions, you have this type of universal structure that is here. These functions, FAB and F, they may not be universal. They may depend on the number of dimensions, or they might depend on the theory, but the general structure is the same. Okay.
Sorry, Alex.
Yeah.
Something I've always been confused about this is that I understand what has been shown, but what I'm confused about is the interpretation. So the statement is that if you look at CIAB, right, there is part of that CIAB, which is a dependence on AB, that is fixed by the symmetries, right? And that's what has been calculated.
No, it doesn't depend just on A and B. It depends on A and B, but also on delta I. So it depends on the scaling dimension of the heavy operator.
Sure, but what I'm trying to say is that there is some sort of this CIAB in the example of two-dimensional CFT is constrained by symmetries of the theory to have a particular form. To my understanding, the calculation does not tell you anything about statistical fluctuations of these guys.
Oh, yeah, I agree. Sorry.
About symmetries.
Yes, so this is very important. So, what these things are giving you they're known as asymptotic formulas for OPE coefficients, right? So thanks. This is a great question. So, what they're telling you is something like this, for example, and this is one that I'll use later in the talk, that the sum over all OPE coefficients where 3 operators are heavy is of the following form. Let me just write it down because so this is like a generalized Cardy formula. It's an asymptotic formula for OPE coefficient densities. But what you're asking, Nima, is absolutely true. What they showed is that, modular invariance constrains the sum of the squares, right? But it does not tell you what the individual things are, or rather how these individual things are distributed. And in fact, this is fixed in all CFTs. So this also applies, in free theories, for example, these types of asymptotic formulas. So the way to think about it is that, these formulas are always true, but the way they're realized is very different from theory to theory. In free theories, you're going to have, huge bumps and tons of selection rules and big jumps in the spectrum. And so there's going to be a lot of substructure. And you'll only get this formula once you average over a sufficiently large band. And in chaotic theories, all this structure disappears, and what we are saying is that it's a lot regular. It's you know, the OPE coefficients, if you want, are sort of evenly distributed, with some random numbers out front that average out once you take the square. And so the way the formula is realized will be highly theory dependent, but the formula is true in all theories. And so you cannot view what they did as a proof of ETH, but rather what they're saying, or a proof of OPE randomness hypothesis, or a proof of ETH for that matter. What you can say is, you know, if ETH is true, then we have a way of computing this function G, or the functions f, a, b, and f here.
So can I say it a little bit differently, and you tell me if you
Yes.
agree or not? If I have a system that has conserved charges, I will
Yeah.
not write straight ETH the way you wrote. I have to modify for the fact that I have charges, right? I have
Yes.
to write down some sort of a sensible, when entropies I'm talking about, I have to say energy eigenstates, I have to fix charges and things like
Yes.
that. Now, once we are talking about a 2D CFD, we have plenty of symmetries. And I'm understanding what these calculations showed us is that the kind of constraints you will have to embed in your correct ETH hypothesis that would conjecture. This is telling you how to conjecture it.
Yeah. So, sorry. We're talking about two different things, I think. What you're talking about is more like the KDV charges story, right?
No. I'm saying that the constraint that you're writing, sum over CIJK has to be this, is a constraint coming from symmetry, right? So this has to be implemented in your ETH conjecture. The same way that if I was doing writing the ETH conjecture for a spin system with a bunch of charges, I will have to put the conservation laws I do know about as an input.
Well, no, I'd say yes and no. I mean, the reason why these things are fixed by, so there's a lot of symmetry in the problem, but you know, what this is saying is that, you know, a thermal 2-point function in a 2D CFT on an infinite line, but at finite temperature, is completely fixed by symmetry, right?
Well, that's a symmetry, yeah.
But that does give you, I mean, if you want, it's a constraint on the OPE coefficients. But I think what it's, one way to think about it is that it's saying that this function G here that we had in ETH, this function G is not universal in all theories. It can be very different from theory to theory. But what happens to be true is that in 2D CFTs, it's the same for all theories.
Which is a consequence of the symmetry. So
yes.
If you wanted to propose a version of ETH that stands a chance, you would have to embed that in your conjecture.
Yeah, okay. I don't really think about it. Maybe this is something that we should discuss
Sure.
at the end of the talk, because it's slightly tangential, but I don't really think about it that way. But maybe you're right. That's a way to think about it. Yes, is that if you built in all the charges that you needed, you would see somehow that this function G, there's no freedom in this function G anymore, that it's fixed. I've never thought about it that way. That's interesting. Yeah, maybe we can come back to this after. Yeah, thanks. Good. Okay, so this is now a statement about 2D CFTs, but what about holography? And so far this was true also, you know, for example, we conjecture this to be true also in the 3D Ising model. So in theories that have no gravity dual, that have a small number of degrees of freedom, but yet are chaotic. So what about holography? And our interpretation is the following, is that basically the semi-classical Euclidean path integral of GR is dual to, or is dual to the OP randomness hypothesis. And what we mean by that is the following, is that, you know, semi-classical GR cannot resolve individual black hole microstates. So the best it can ever hope to do is treat them statistically. And so really, you know, GR does not have access to these precise values of the OPE coefficients or the precise values of the spectrum, but rather at best has access to their statistical distribution, to their moments. Okay. So for example, if you imagine that you're trying to compute some quantity that involves some OPE coefficients or product of OPE coefficients that I'm going to label schematically by some, you know, index I as a function of this index I. Well, as we said, you know, in a chaotic theory, we expect these things to be crazily distributed all over the place. And GR can never resolve these numbers, but what GR can do is, extract the mean or extract the envelope, which is the variance, and in principle, all higher moments. Okay, so it treats these things statistically, but by treating them statistically, it makes a mistake because, as we said, these things are not actual random numbers, they're quasi-random. And by treating them statistically, it makes a mistake, and this mistake is basically given by the wormholes, which then explains the lack of factorization. Okay, so if it makes a mistake, and this is where wormholes come in. Yeah.
When you said quasi-random, did you mean it in a rigorous sense, or is that just you meant it colloquial?
No, I don't know if there's a mathematically rigorous sense for this type of thing. It's quasi-random in the same sense as I was talking about.
Yeah. Okay.
Yeah. Meaning that in any given CFT, in principle, these OPE coefficients they're not random. They're numbers, but they're statistically distributed in some way, and GR only has access to the statistical distribution.
Thank you.
So in other words, it has access to these functions f, fab, g that we saw before, but that's it. So this is the proposal. And well, I see that I'm sort of way behind, and I think I'm only going to go through one of my applications.
Alex,
but I should have 5 more minutes at least, right? Because I started late.
You have many more minutes, so feel free. I think if people want to leave, they can leave. But yeah.
Yeah. So I'll go through application 1. That should not take me too long, and then I'll stop, and then you can ask me about application 2 in the questions maybe. So application 1 is to discuss the genus 2 wormhole, which was one of these wormholes that Maus and Maldacena discussed in their paper reporting on the lack of factorization. So this wormhole is a wormhole in 3D gravity with a negative cosmological constant. And it's so simple that I can even write down the metric for you in real time. And the metric is just the following. Where d sigma is just a constant negative curvature metric on the genus 2 surface. And so, this geometry asymptotes between 2 Euclidean boundaries that are genus 2 surfaces. So you would think that this thing would contribute if you're trying to compute the product of genus 2 partition functions. Okay, so if you're trying to compute the product of genus 2 partition functions using gravity, well, what would you get? You would, first you would have disconnected solutions, which just correspond to filling in some of these cycles. These are called handle body geometries. They're like the generalization of BTZ to higher genus, where you just fill in some of these cycles in the bulk. Okay, and you would have disconnected geometries of this type. So you would have 2 disconnected handle bodies, and then you would also have this Euclidean wormhole that connects the 2.
Sorry, let me confirm.
Yeah.
Is the genus 1 case trivial? Doesn't teach you anything new? Is that why you jumped to?
Yeah, there are no wormholes. There are no saddles that have vanishing curvature or positive curvature. So the simplest geometry that you can find, which is a solution to the equation of motion, requires negative curvature on the cross section, if you want, and that's genus 2. So a genus 2 surface.
There are no 3 manifolds that fill in between 2 tori.
That are solutions? No. Yeah.
Oh,
there's
wow.
definitely field configurations, but there's no saddles.
Not even complex saddle. Yeah.
No, not even complex saddles. Yeah.
Wow. Okay. Thanks.
And Culler and Jensen have a series of papers where they discuss how you could try to still compute those configurations. So, in principle, when you do the path integral, you don't just sum over saddles, you sum over all field configurations as well. And they have some technology called constraint instantons where they still try to, take into account these geometries, but they're not saddles to Einstein. They're not solutions to Einstein's equations. But they're also interesting to consider. Okay, and so
the genus 2 has some moduli, so you can take any shape, or you can take some specific genus 2 surface.
Yeah, this geometry works for any of the choices of the moduli of the surface. You see, we're just putting a constant negative curvature metric on it, And so you can move the moduli around as you wish, and this geometry exists.
No, but then you were gonna do some calculation or something.
Sorry?
You're gonna do some calculation now, I guess, or?
Oh yeah. I haven't. Yeah. Thanks. I haven't written down what the answer is of the partition function. Absolutely.
No, but that's work for any moduli. I mean, what you're gonna do.
Yeah. No, I'm gonna do something. I'm gonna do the simplest possible thing that I can do. So I'm gonna take, all three. So the genus 2 surface has 3 complex moduli, which you can think about as 3 sort of temperatures. I'm going to take all 3 of them to be the same, and I'm going to look at the limit, which is kind of like a pinching limit where the temperature goes to infinity, or the cycles become very, very thin. And that's the only situation in which we have control over the on-shell action. It's not a conceptual problem. It's hard to evaluate these on-shell actions, and it's only in this limit that we can do it.
Thank you.
Yeah, thanks. That was another great question. And so in this limit, again, we get the following. The handle bodies, their contribution is the following. And then it turns out that the on-shell action of the wormhole is actually easy to compute because it vanishes. So we just get a 1 here. But really this 1 is a bit misleading. It's happening because we picked the same moduli at the top and at the bottom. So imagine we had picked different ones for a second. Here would have really been the place where the function of beta and beta prime is hiding, and which is responsible for the lack of factorization. So even though I'm writing a 1 here, you should view it as an avatar of the lack of factorization. Okay, and now the question is how can we reproduce this in the CFT? Great. Now, obviously, if we just do a microscopic CFT computation, and I guess this is kind of what Nima was saying way earlier in the talk, if we do any microscopic computation, well, we're never going to reproduce this because, in the CFT, we just get an answer that manifestly factorizes. But that's not what we're going to do. What we're going to do is compute this thing using the OPE randomness hypothesis. Okay, and just, yeah.
Thanks for interrupting again.
Yeah,
so
please.
The fact that there are no saddles for Taurus, genus 1, that just means that some calculation is 0 or something. Does that have any implications? Or could that be interpreted?
I think the way I would say it is that, if you wanted to compute the connected Euclidean path integral between 2 tori, is that we would not know how to evaluate that path integral. Because you can clearly write down metrics that asymptote between the 2, but they're not on shell. So I don't know how to sum over them in any nice way.
No, that's fine. But here also you're going to do some sort of saddle point approximation, which means that you're not going to sum over off-shell stuff anyway. So you're assuming that you're discarding them anyway, right? So there's some sort of an approximation. Within that approximation, the absence of a saddle in between 2 tori, does that have an implication or not? At the same, in the same approximation?
Yeah, I think it probably does. I think nobody knows exactly how to think about that. So one way to ask that question is, we got the ramp in 2D gravity, but how do we get it in 3D or higher dimensions? And the problem is that this Euclidean wormhole doesn't exist as a saddle in those cases. And so I'd say it's somewhat of a puzzle. We don't exactly know what we're supposed to do. What I'm doing here is slightly better because I'm just picking a wormhole that does correspond to a saddle. So it is a solution to the equations of motion, which can be stable, so it's a valid saddle. And then I'm asking,
for being nitpicky, but I guess I want to ask it a little bit differently.
Okay.
If I were to do a calculation in a CFT, would I have deduced that in gravity there will not be a saddle point approximation connecting the two? I allow you to use ETH. I allow you to say all.
No.
Would you have deduced it?
Very good, thanks. Yeah. So I think the answer to that is no. You wouldn't have really known. I think the way this works is that it's a bit more reverse engineering. It's sort of we're using gravity. We're using the cases where there is a saddle to infer the distribution that you're supposed to have in the CFT. But there's no first principles way to know in the CFT what these distributions are currently, and to the best of my knowledge.
Okay, so it's not like some sort of fancy large C2D calculation that will reproduce this.
No, no,
Okay, thank you.
not that I know of, at least. Yeah. Great. Yeah. That's an excellent question again. So this is what we're going to do. And before we do that, I just need to tell you quickly how we compute a genus 2 partition function in a 2D conformal field theory. So what we do is we sum over 3 copies of the states. We multiply by the OPE coefficient of these 3 states squared. And then there's sort of the equivalent of the Boltzmann factor for genus 2, which is just the sum of the 3 weights of the 3 operators. Okay, so, and again, this is for very special moduli where all 3 of them are the same. Some very special slice of moduli space. And so you can view this as a sort of generalized thermal partition function, a Boltzmann sum, but that is weighted now by the OPE coefficients. Okay, so let's try to compute this using the OPE randomness hypothesis. So I'm going to write it in some somewhat complicated way, but just bear with me. So I'm going to write it as a sum over many states with particular delta functions, Kronecker deltas that are ensuring the right contractions of the indices. Here we go, QT. And then there's 4 OPE coefficients because there's 2 of them in each genus 2 partition function. Okay, and then there's this Boltzmann factor with the sum of all the weights. Okay, and I'm writing it on one line in some very complicated way, but because of the way the Kronecker deltas are here, this is just, this thing you could separate and show that these are clearly 2 different sums that don't talk to one another. Okay, so this is a factorized thing. But we're not going to compute it exactly. We're going to compute using the ansatz. And remember, I told you these things are Gaussian random variables to some leading approximation. And so we're going to use this Gaussian distribution, which basically corresponds to doing Wick contraction. And the first thing that you can do is do just this Wick contraction. And you use the formulas for the Gaussian part, this function f that I wrote a few slides back. You do a saddle, and I'm going to spare you all these details. And what you get is just the following answer. Okay, this is coming from the green Wick contraction. And this is sort of this is the square of what you would have gotten if you had just looked at the disconnected part. But there's another Wick contraction where you can contract this OPE coefficient with this one and this one with this one. And here the powers of the entropy, the number of states that you need to sum over when you do this Wick contraction is different. And here it happens that there's no longer a saddle in these sums or these integrals over scaling dimensions. There's no saddle anymore, which really means that the large exponentially growing piece has disappeared, and really we're left with a 1. Of course, there's a function here that in principle we could calculate, but there's no exponential piece. And this is coming from the red contraction. Okay, and the structure here actually exactly matches what we found in gravity. And again, just like before, if I had picked, if I had written something like this, beta I plus j delta k e to the minus beta prime delta O plus delta P plus delta Q. Here, there would have really been a function of beta and beta prime here, which again would have been responsible for the lack of factorization. So what we're seeing here is that using the OPE randomness hypothesis and the leading Gaussian distribution, when we compute the square of partition functions, there's another type of a contraction that you can do, another Wick contraction, and that seems to be giving us the wormhole contribution. Okay, and again, this does not match. So what we compute using the OPE randomness hypothesis does not match any microscopic calculation because it's approximate. We're using the ansatz. And here we seem to match what gravity gets and what the wormhole gets. And so I'm already quite a bit out of time. I don't want to go on any longer. I'm not going to talk about the second application. But just to summarize, so what we proposed is an extension of the ETH ansatz in chaotic CFTs called the OPE randomness hypothesis, and it treats all heavy operators as random variables with some, to leading order Gaussian distribution that you can sometimes extract. And what we showed is that, using this ansatz, if you compute the square of genus 2 partition functions, you get an answer compatible with what gravity gives you. And in particular, you reproduce at least at the level of the on-shell action, you reproduce the wormhole of Mouse and the genus 2 wormhole of Mouse and Maldacena. And so, yeah, let me not go any further for now, and thank you again for your attention.
Thanks so much, Alex, for the wonderful talk.
Let me just turn on the light. It's getting very dark here.
Are there any questions?
I have a question about this last point, because I guess if you think the other way, one might say, okay, if I compute more wormholes and I sum everything, then it will factorize, or I compute fluctuations. But here you are saying, I mean, it's like there is no clear mechanism how to undo this random average, or like if you do it more I mean, I would expect, yeah.
Yeah, so there's a question of how do you restore factorization? And I guess we don't know for sure, but we don't expect factorization to be restored strictly within the low energy semi-classical theory. Probably to restore factorization, you need to add in strings and branes and all kinds of complicated UV objects. And those UV objects are what are going to give you the exact, erratic signal. But you probably cannot restore factorization just from low energy EFT. You probably need a lot of UV structure.
But in your second approach, where you do this average, you can say, can you do that in a controlled way, saying, okay, I'm going to average this, but then if I add these corrections, then I will get when you contracted in this slide, the green and the...
Here, yeah. How would you undo this in some sense?
Yes, so, okay, I did this approximation, but I have these extra terms that if I sum, then it will...
Right, right, good. So this extra term is like a diagonal piece where basically all indices are the same. Yeah, so what you're supposed to do to restore the full factorization is restore the off-diagonal terms, basically. There's some off-diagonal terms that we discarded this way. And we don't know how to do that precisely, but the idea is that, the branes and strings would be what are making these off-diagonal terms.
These are supposed to be very small, but there is a lot of them, or what's going on?
Yeah, eventually, exactly. That's the idea, yeah. Exactly, they're very small, they're exponentially small, but there's a lot of them, and on top of that, statistically, they vanish when you average, or they're further exponentially suppressed when you average. But really, when you're trying to reconstruct the exact signal that factorizes, then you need all of them. That would be the idea. But I mean, this is a bit of a cartoon, and we don't know how to make that precise. Yeah.
I do have a question as well, just to understand your last slide. So this is the conjecture you guys make, is it for any chaotic CFT, or is it just large C?
No, what we believe is that it's true in any chaotic CFT.
Then what you calculated is a statement that's true for any chaotic CFT, and you found some sort of a wormhole corresponding to any chaotic CFT, right? Because
no, sorry, yeah. So sorry, there's several steps. This we expect to be true in any CFT. This stage here.
That's just modular invariance. I agree completely.
No, but sorry, the structure here, the fact that these things are basically random variables or quasi-random variables. This is expected to be true, yeah. And then this is fixed by symmetry. But already here, what I did is this is not the full expression. I took already a large C approximation for this expression here.
But can't you do the exact one? Doesn't it, is it known? I thought this was known. Like C goes to C minus. No. Sorry. That's not.
Yeah, there's various corrections that are known. I don't know if I would say that the exact thing is. There's a lot of control over it. Yeah.
But you think that in your calculation, large C played an essential role?
It did, yeah. Because I did saddles, and large C does play a role in keeping certain saddles.
So does high temperature.
Yeah, high temperature can help you as well. Yeah.
I mean, for chaotic CFT that's not large C, the small parameter would be beta, right? and then
Yes.
you some other expression. So that's why I actually wanted to ask this question. That when you say, I mean, it would be, yeah, I guess it becomes the question becomes this f beta prime you write down.
Yeah.
In the beta going to 0 limit, how does
Yeah.
it behave? Does it,
Yeah,
does
we
it then
don't
grow
know. Yeah.
exponentially? Because if it grows exponentially, then yeah, this is this evidence for, yeah.
Well, I think the honest answer is we don't know. From the gravity perspective, what f of beta and beta prime is a one loop determinant of the fluctuating fields on top of the geometry. But that's a large C statement, right? So
yeah.
So I don't know. And then, you know, at next order in 1 over C, then it becomes a two loop thing, a two loop diagram, and then so on and so forth. And so I don't know if you can, the fact that you can have access to this function at all, that's a large CR statement. Otherwise, I don't know how to even think about this function.
But I'm somewhat conceptually confused, because if you did say you were more powerful, like you knew a lot of 2D CFD, or in the future we will figure this out, then we could do this calculation for a finite central charge CFD at large temperature, right? You would still find contribution that doesn't, you will see the failure of factorization. There will be a term that you will associate to, you know, failure of factorization. And I believe that term is going to be exponentially suppressed compared to the dominant factor piece. So what is exactly
listen, I think you're more optimistic than I am. And I think this is not completely crazy to say these words, because remember, something like the ramp is not only true in large C theories, right? The ramp we expect to be true also for a spin chain or something like that. So, you know, maybe there's a sense in which certain things that you're extracting, even when there's no geometry really, maybe there's like, you know, an auxiliary geometry that is there, and you can compute wormholes in it, and it gives you access to something, even when the CFT has no real bulk dual.
But what I was gonna say is that your calculation is evidence for the ramp, right? But, and also there is another piece of thing, with another fact, which is Euclidean wormholes are related to a ramp.
Yeah.
Right? So I think, yeah.
I'm sympathetic to that. I'm not sure. I'm definitely sympathetic to that. The question is really how strongly you can control all the things that we did. And so, you know, all these asymptotic formulas, they have 1 over delta, which, you know, are basically like 1 over T corrections, but they also have 1 over C corrections. And so, you know, one would need to, they have both, and they have delta over C, they have all types of corrections. So, you know, if we were very powerful and we could resum all the 1 over C corrections somehow and still have the calculation under control, then yeah, maybe it would be okay. And it's teaching us about small C theories that are chaotic. It's possible.
I mean, the main question, maybe turned around, becomes something like this. You're connecting this the chaotic behavior of OP coefficients to some sort of an EFT. Now, I would say I expect an EFT to exist for any chaotic CFD, central charge large or not. And then that would have some sort of you could construct auxiliary geometries in the bulk, right? Now, bulk, right? There won't be Einstein.
Now it's a bulk in this sense.
I mean, there won't be Einstein's equations, but these are, there's a partition function you could construct. And the game is the same, right?
Yes.
You could construct your effective field theory order by order in perturbation theory. And I think, at least at the very low level, we argued for this, but you guys have done much fancier stuff.
I think I'm sympathetic to that reasoning. Yeah. That's the most optimistic thing you might hope, is that actually, you know, you're deriving an EFT, which turns out to be connected to GR. It's only the real geometric bulk at large C, but there's still an auxiliary geometry that's valid at small c that correctly captures some of the features that you're trying to see. That's possible, and that would be even more exciting in some sense. But yeah, no, I'm definitely sympathetic. Yeah.
Are there any other questions for Alex?
I had one. Thanks for the talk. I don't know if this is a silly question. Maybe it's not even worth thinking about, but so you have an ensemble of OPE coefficients, and each member of the ensemble gives you a good CFT. And I was just wondering if you average the coefficients over the ensemble first, and then try and construct a theory from those averaged coefficients, is there any sense in which the result is worth thinking about, or if it gives a good field theory in any way, or if you can measure it from the gravity side or something like that?
Yeah, as often when people start with, I'm not sure the question makes sense. It's often, those are very, very good questions and sometimes hard to answer. I'm gonna maybe answer in a slightly different way than maybe what you had in mind, but there's a question that you can ask is, okay, we said that these OPE coefficients are quasi-random, but is there a sense in which we can actually make them random? Or in other words, can we make the OPE randomness hypothesis exact? Or could we make ETH exact? And presumably that involves averaging now over Hamiltonians, because otherwise, as we said, they're definite numbers. But if you really want to treat them as, you know, as random, then you need to average over Hamiltonians. And maybe there's a way to do that that's consistent with the bootstrap. So, you know, maybe there's a way that you can find something which is not a legit CFT, but is like a statistical CFT in that, you know, it satisfies all the bootstrap constraints statistically, but there's not a discrete list of operators. Mm-hmm. And maybe if you do that, you can make the OPE randomness hypothesis exact. That would be really exciting. We certainly don't know how to do that. I think, like I was saying earlier, I think even for ETH, it's not completely clear. There's more in ETH than just random matrix theory. And I don't think people know how to systematically put the two together, or yeah.
Do you expect something like that should be possible, or is it sort of an open question as to whether...
I think it's an open question. One thing that you can certainly do is you can, sorry for going over this fast, but you know, you can take your CFT and you can deform by the 't Hooft coupling. Say this is in 2D. So sorry, it's yeah. So it's this, and then you can start, and then you can integrate this over lambda within some window and maybe some profile of lambda, maybe using the Thermalization metric. So you can average over couplings in the CFT. That can make sense. That's what people have done for Narayan CFTs. Those are very simple, but you could try to average over the 't Hooft coupling. And when you'll do that, you'll produce actual randomness. I mean, now the factorization is no longer a puzzle. It's a feature because you've averaged over theories. And you can try to see if doing something like this can make the OPE randomness hypothesis exact, or maybe not quite exact, but closer to exact, or closer. And these are great words. It's just, I don't know how to do any of this in practice, but it's certainly an interesting and open question. Yeah, thanks.
Thank you.
Are there any other questions? If not, let's thank Alex again for the wonderful talk. And yeah, thanks for all of you guys. This was the last seminar of this semester for us, and we'll come back later next semester. Thanks so much, Alex.
Great. Thanks a lot, guys.
All right.
Have a good day.
Bye.
Bye.
Thank you. Bye.
Thank you. Bye.